So a gravitational wave is a particular kind of distortion of space-time. Einstein had this stunning insight about 100 years ago that gravity can really be thought of as a warping of space. So the area around our sun and around our Earth is a space that has been warped by the presence of the sun and the Earth. They bend the space around them. And objects that are in the vicinity of these very massive objects will respond to that. So this is a two-dimensional model of three-dimensional space-time. So what we have here is a rubber sheet. So if I press on the rubber sheet, I distort it. If I imagine that an object like a planet is traveling through outer space, it'll go in a straight line, just like that. But now, if I warp my space by pressing, in this example, then I distort the trajectory that that planet takes. And in particular, if I place a very heavy object, this represents, say, the sun, and I have a planet going around the sun, I can think of it in this way. It's traveling around the sun in an orbit that is affected by the warping of space. Now, here we have this warping of space, and if I take this sun and I jiggle it like this, I'm creating ripples. Or if I do this, imagine I have a very violent event like a supernova that suddenly disturbs space, then you can see that there are ripples being created in this rubber sheet, and there are analogous ripples created in space-time itself, and those are what we call gravitational waves. Einstein predicted gravitational waves, and he predicted the properties that they would have. For example, there is this characteristic stretching in one direction that is simultaneous with a compression in the other direction. That's what space itself is doing as a result of the passage of a gravitational wave. We have, for the first time, detected gravitational waves with our interferometers, the LIGO interferometers. All right, so here we have a model of LIGO, a highly simplified model, but it contains the essence of what LIGO does. So here we have a laser. It shoots a beam of light this way. That beam of light hits what's called a beam splitter, which has a property, it's basically a piece of glass, but it has a property that half the light goes through and half the light gets deflected in this direction. Now, we also have a mirror up here that sends the light back toward the beam splitter, and we have another mirror here that also sends this light back to the beam splitter. Now, this beam splitter has a property, as I said a moment ago, that half the light goes through and half the light gets reflected to the side. Now, if you arrange so that the distance between this beam splitter and this mirror is exactly the right amount compared to the distance between the beam splitter and this other mirror, you can arrange for all of the light to go back toward the laser and none of the light to go in this direction toward the detector. Now, why in the world would you do that? Why would you not send light to your detector? Well, the reason is the following. If we can set this up so that normally all the light that's reflected back from these two mirrors goes back toward the laser, then if a gravitational wave passes through this interferometer, it will, for example, stretch this arm a little bit and compress this arm a little bit, and that will disturb this delicate balance that we had a moment ago. And as a result of that, some of the light will pass through toward the detector, and we will see a little brightening of the light, which we detect as an electronic signal. We measured a distortion that we call a quadrupolar distortion. That is exactly what you would expect from a gravitational wave. And the shape of the waveform that we saw, which only lasted 0.2 of a second, but had a very characteristic shape, that shape is exactly what you would expect from two black holes spiraling in and colliding with each other. And that's something that we can predict with high accuracy, and we've been able to verify that our waveform matches that prediction very, very well.